Welcome to Howard's math lessons. I hope everybody had a good New Year. And today we're going to be going over the proof that the derivative of e to the x is equal to e to the x. So a refresher on what a derivative is that a derivative is basically the rate of change for a function. So you can think about this as, for example, on a car, let's say this is the number of kilometers, and then this is the time, right? And basically when you drive, you're going to be going like fast and then slow, or it wouldn't go down, but fast and then slow and then fast again. And then what the derivative basically tells you is that at this specific time, so let's say this is like 2 hours after you started driving, you're going at this specific speed, right? And that's what your speedometer tells you, okay? And if we remember, the function e to the x, like this, its rate of change, so the change that it's at this time is equal to whatever this is, which is a really interesting property in math, and one of the reasons why the the number e is so special. Okay, and this was actually one of the questions on my math test. I think at the start of last year, the start of grade 12. And I thought it was a really cool question, and it basically walks you through how to prove this identity step to step. Okay, so let's start with the first step, which is starts with a definition. So we know E, this is just by definition, equals the limit as n approaches infinity of 1 plus 1 over n all to the power of n. So basically, the limit is just as this function approaches infinity. So in this function, as n approaches infinity, we get this number e, right? And basically after that, we have using the substitution m equals, yeah, uh, we're basically going to substitute a variable now. So the second part of the question goes, so we have to use the substitution h equals 1 to the n to show the fact that limit as x approaches a of f to the g of x equals f of limit as x approaches a of g of x. Okay, so let's see here. Use a fact. Okay, sorry. So we have this substitution and we have this fact, and what we're trying to prove is that limit as h approaches 0 of the natural logarithm of 1 plus h over h equals 1, right? Now this may seem kind of random at the start, but it'll, after you see the entire proof, it'll make more sense, right? So let's see. The first thing we should do is we should go back to our original definition here, which is that e equals the limit of n approaches infinity of 1 plus 1 over n to the power of n. Now, we see, okay, where was it? if h equals 1 over n, then as n approaches infinity, what does 1 over n approach? It approaches 0, right? If, let's say it starts at 1 over 10, goes to 1 over 100, and then it keeps going. It keeps getting smaller and smaller until it approaches 0. So we know that limit as n approaches infinity, we can substitute h, then limit of h, then this is the same as saying as h approaches 0, right? These two are the same statement. So we can also rewrite this top part as 1 over h, because h equals 1 over n, so 1 over n would be basically just n, right? So 1 over h, and then we can substitute the rest in, so limit as h approaches 0 of 1 plus h was 1 over h. And we just take the natural logarithm of e, which is 1, equals the natural logarithm of whatever this is, right? And bring this back up here. We use this fact again. So we bring the ln, or the natural logarithm, inside the limit. So 1 would equal limit as h approaches 0 of the natural logarithm of 1 plus h over 1 over h. And this, of course, using our exponential laws, we can bring the 1 over h down to get the natural logarithm of 1 plus h over h equals 1. And boom, you just got in 2 points, 2 marks on the test, right? So we have this statement. Let's see what we must do next. So the next thing you have to do is using the substitution, okay, m equals natural logarithm of 1 plus h. We have to show that limit as m approaches 0 of e to the m minus 1 over m equals 1. Okay, so let's write this out. So let's start with this statement. Limit of m approaches 0 of e to the m minus 1 over m. And let's see. We know that m equals ln 1 plus h. So let's substitute that in. Ln as m approaches 0 equals e to the ln 1 plus h. Minus 1. Oh, sorry, this should be down here. Over ln of 1 plus h. Now, again, we have to see. So as m approaches 0. So as ln of 1 plus h, as this statement approaches 0, what value does h have to approach, right? Well, we know that ln of 1, ln of 1 equals 0. So for this statement to approach 0, it has to approach, the inside part has to approach 1, which means that h has to approach 0. So we can change this m to a h, okay? And now we bring this down, so ln of h approaches 0. These cancel, it's just 1 plus h minus 1 over the natural logarithm of 1 plus h. And we get the limit as h approaches 0 of h over the natural logarithm of 1 plus h. Yep. And let's see. And from here, we have to do a little bit of, so we can bring this h down here. So if we divide the top and the bottom by 1 over h, so basically we're multiplying top and the bottom by 1 over h, this part cancels out to 1, and the bottom part cancels to this, right? And once again, we use our log laws to bring that 1 over h to the top. And if we see this and we look back above, so the limit of as h approaches 0 of 1 is just 1, right? What is the limit of h approaches 0 of ln 1 plus h, 1 over h? Well, let's look back up here, or back on this page. It is 1, so it's just 1 over 1. And we have proven the question. So yeah, another 3 marks. And let's keep going. B or C. So all these parts are going to come together in the end to prove that the derivative of e to the x is e to the x. And that's actually the next part. So we know, so using the formal definition of a limit, which is limit as h approaches 0 of f of x plus h minus f of x over h equals, equals the derivative of that function. Using this formal definition, we're going to prove that when f of x equals e to the x, f of derivative x equals e to the x. Okay? So f derivative of x equals limit as h approaches 0 of f of x plus h minus f of x over h, and this would be limit h approaches 0. Since x plus h, f of x equals e to the x, then it will be e x plus h minus e to the x over h. And what we can do is we can take out a common factor of e to the x. So e to the x and then h minus 1. And this part is h. And yeah. Wait. And since we're talking about the limit of h approaching 0, e to the x doesn't matter. So we can just take that out, right? Because there's no term that has h in this part. So it doesn't matter that h is approaching 0. It'll always be e to the x regardless. And then we have this limit as h approaches 0 of eh minus 1 over h. And now we can look back on this last part. E to the m minus 1 over m equals 1. And now we just replace h or m with h. So that would also equal 1. And boom, using the formal definition of a limit and these properties from before, we have proven that the derivative of e to the x is e to the x.